What if a new kind of computer could solve problems in seconds that classical computers would take millennia to crack? Welcome to quantum computing. It's not science fiction, it's happening now. For example, Google's quantum processor was reported to achieve in minutes what would take a supercomputer 10,000 years. That leap in speed could change everything from how we encrypt data to how we discover new medicines. Today, we'll demystify quantum computing and explore how it's poised to transform technology.
Quantum computers.
Quantum technology.
What on earth is a quantum computer?
Bits, qubits. Try all the codes at once.
Whichever nation first develops a practical quantum computer will have a tremendous advantage.
Quantum supremacy.
In this video, we'll break down quantum computing in simple terms. No PhD required. First, the basics. What makes a quantum computer different and powerful compared to your laptop or phone? Then, how it works, superposition and entanglement. Next, real-world applications, from code breaking to drug discovery, and why it's a game changer. Finally, where we are now and what's next, including the biggest challenges. By the end, you'll understand the tech and why companies and governments are in a quantum race. Quantum Computing 101. Qubits versus bits. Traditional computers use bits, 0 or 1. Quantum computers use qubits, which thanks to quantum physics can be 0, 1, or both at the same time. Think of a bit as a coin lying heads or tails. A qubit is a spinning coin. A heads and tails blur until you look. Groups of qubits can represent many possibilities at once, unlike classical bits. Qubits can also be entangled, so the state of one instantly correlates with another, even far apart. Superposition plus entanglement enables coordinated, massively parallel calculations for certain tasks. While two classical bits are in only one of 4 configurations at a time, 0, 0, 0, 1, 1, 0, 1, 1, two qubits in superposition can effectively explore all 4 at once. 10 qubits span 2 to the power of 10 equals 1024 states simultaneously. With 50 to 100 well-controlled qubits, specific problems could outpace classical machines with billions of bits. The catch: qubits are fragile and can lose their quantum state from tiny disturbances. That fragility is central to the challenges we'll cover. How quantum computers work, no heavy math. A typical system sits inside a dilution refrigerator near absolute zero because quantum effects are delicate. Heat and vibration disrupt them. There are multiple qubit technologies. Superconducting circuits, used by companies like IBM and Google, trapped ions, e.g. ion Q, photons, and diamond defects, ENV centers. Each approach has trade-offs, but the goal is the same: create controllable, entangleable qubits to run algorithms. Quantum computers don't just run the same code faster, they solve certain problems differently. A famous example is factoring large numbers, the basis of much modern encryption, which a quantum algorithm, Shor's, could tackle exponentially faster. They're also promising for optimization and simulation, especially simulating molecules and materials, because chemistry is inherently quantum. A computation starts by preparing qubits, applying a sequence of quantum gates operations that rotate states and create entanglement, and then measuring them to get classical zeros and ones. The art is designing gate sequences so wrong answers cancel and the right answer emerges with high probability. Because qubits are noisy, results can have errors. That's why researchers pursue quantum error correction, combining many physical qubits into one more reliable logical qubit to run useful programs longer. Why it matters: real-world impact and applications. Cryptography and cybersecurity. A large fault-tolerant quantum computer could break widely used encryption, e.g. via Shor's algorithm. So governments and companies are moving to post-quantum cryptography. Quantum tech can also secure data with quantum key distribution, where eavesdropping is detectable. Drug discovery and chemistry. Classical computers struggle to simulate complex molecules. Quantum systems can model molecular interactions more naturally, potentially speeding up discovery of new medicines and materials, from years to far faster timelines, by testing interactions in silico. Finance and optimization. Many financial problems are optimization under uncertainty: portfolio construction, risk analysis, pricing. Quantum algorithms, such as variational and approximate optimization approaches, could explore vast combinations more efficiently. Quantum methods may also help detect fraud via subtle pattern recognition. AI and machine learning. Research is exploring quantum-enhanced ML, speeding parts of training or finding patterns more efficiently. It's early, but the idea is to evaluate many possibilities at once, potentially improving everything from forecasts to recommendations. Logistics and traffic. Quantum optimization could improve routing, scheduling, and distribution, reducing congestion, streamlining supply chains, and speeding deliveries as cities generate ever more data. Science and climate. From modeling climate systems with higher fidelity to simulating fundamental physics, quantum computing could accelerate discovery across domains. The road ahead. Challenges and breakthroughs. Error rates and qubit quality. Qubits are finicky. Quantum error correction aims to bundle many physical qubits into robust logical qubits, but it's resource intensive. Millions of physical qubits may be needed for large-scale applications. Today's devices have on the order of tens to a few hundred noisy qubits. Scaling up, moving from small devices to thousands of controllable, interconnected qubits is a major engineering challenge. Control wiring, cooling, crosstalk, and architecture. Progress includes chips exceeding 400 qubits and efforts toward modular, networked designs to scale more manageably. Software and algorithms. Hardware needs matching software. Beyond landmark algorithms like Shor's and Grover's, researchers are building methods that tolerate noise and hybrid quantum classical workflows. Toolkits, e.g. for programming real quantum processors via the cloud, help broaden experimentation. Competition and collaboration. The US, Europe, China, and others are investing heavily. Tech giants and startups, IBM, Google, Microsoft, Intel, Amazon, IonQ, D-Wave, Rigetti, and more, are advancing different approaches. The focus is shifting from one-off supremacy demos to quantum advantage, useful tasks classical computers struggle with. Many experts expect industry integrations this decade in niches like drug discovery and complex optimization, and governments are already planning quantum-safe encryption transitions. Staying grounded. Quantum computers won't replace classical ones. They'll likely live in data centers as specialized accelerators for hard problems, with most everyday computing staying classical. More qubits don't automatically mean more utility. Error rates and coherence matter. But as hurdles fall, breakthroughs should accelerate. Quantum computing is often called the next frontier of technology, and for good reason. It forces us to rethink what computing even means, leveraging the strange rules of physics to tackle problems once thought impossible. Today we learned that qubits can be 0 and 1 at the same time, that quantum machines might one day crack our codes and cure our diseases, and that there's a lively global race to overcome the challenges and fully unlock this power. It's an exciting time. We're witnessing the early days of a technology that, by 2030 and beyond, could fundamentally reshape industries and research. Just as electricity or classical computers changed the world, quantum computers could spark a new revolution in how we process information. What do you think? Are you excited about the possibilities of quantum computing, or does it seem a bit intimidating? Let's discuss. Drop a comment with your thoughts or questions. I'd love to hear your take. If you found this explanation enlightening, smash that like button and subscribe for more deep dives into the tech that's shaping our future. Thanks for joining me on this quantum adventure. Until next time, stay curious and keep looking to the future.